Great. Well, thank you, Brian. That's a very generous introduction. Appreciate that. And I want to thank Father Conrad and the Aquinas Institute for the invitation and for the hospitality this term as I've been visiting on sabbatical. It's been really tremendous, and it's a great privilege, and a privilege as well to be able to talk to you all this morning about this. Father Conrad did a great job setting up my talk. I almost feel like I could sit down now and say, yeah, that's exactly what I wanted to say. I think one way to put it is that a lot of Aristotelian baby was thrown out with the bathwater in the scientific revolution. I mean, obviously, there's lots of things about Aristotle that have to be changed. There aren't any crystalline spheres, sadly, 5 elements, and so on. But if we try to isolate the things that are the truly fundamental elements of Aristotle's thought, then I think we'll find that these were abandoned in the scientific revolution. But when the quantum revolution came along, had they still remembered those things, they would have said, this is easy. We can now make sense of this quantum stuff. And so much of what people call the mysteries of the quantum revolution are mysteries only because you've rejected the Aristotelian framework and are working within a kind of narrow, reductionistic, materialistic kind of picture. So in fact, the quantum revolution is the great vindication of Aristotelian philosophy, I'm going to argue. So in this talk, it's going to be very non-technical, so I hope that's not disappointing to most of you. I think there'll be almost no mathematics in it. I'm just going to talk about things in a very qualitative way, again, kind of stepping back and trying to look at the big picture, how Aristotle's philosophy relates to, okay, let me see if I can figure out which button I need to push. Good, yeah. So I'll spend a few minutes at the very beginning talking about what was Aristotle's vision of nature. Well, I should say, why is this relevant to a Thomistic Aquinas colloquium? Well, obviously, right? Because Thomas, as Father said, is drawing heavily on Aristotle's philosophy of nature. And so if we're going to be able to relate Aristotelian Thomistic philosophy, Thomistic theology to modern science, we need to look at that framework. So I'll give a quick overview of that. Then a few minutes on the anti-Aristotelian revolution of the 17th century, and then the quantum counter-revolution, and then finally back to the Aristotelian future. So this is where the meat of the paper is going to be, how the Aristotelian framework can help us make sense of the quantum world. Okay, so Aristotle's vision of nature. We'll talk briefly about 4 elements: formal and material causation, bottom-up and top-down sort of causation in Aristotle, causal powers and change, the idea that change occurs not because of abstract laws of nature, but because particular things have natures themselves and cause change that's always directed in a particular way. And that leads sort of naturally to the idea of teleology, which I'll explain. That once you have directed change, you have ends. You have teleology built into nature. And this means that we have real agency at multiple levels, that is, at the chemical and the biological and personal levels, as well as at the microphysical sorts of levels, according to Aristotle. So, again, formal and material causes. In Aristotle's picture of the world, we have both bottom-up and top-down factors that take into account. Matter is the bottom-up sort of constraint. Form is top-down. Form makes composite material things to be the kind of thing that it is. Right? It confers active and passive powers on the whole, internal powers of change and stability. Right? So there's an essential top-down feature here. Right? Things have form that makes the parts be what they are and act the way they do because of that holistic form. Material composition, involving having the right kinds of parts and in the right spatial relationship to each other, that's a necessary condition, but never a sufficient condition for the substance to be the kind of thing it is. In addition to that, you need the form, right? Which provides them with their per se unity, makes it into truly one thing. Now, as I said, the form confers causal powers on the whole and also on the parts. So things change as a result of the intermeshing of these active and passive powers and potentialities. Things have a power to cause change in other things, and things have the potentiality to be changed as a result of the interaction between substances. So time advances on Aristotle's picture because things change and not vice versa. This is, I think, a very important thing to bear in mind. So instead of, as in the modern picture, where you have time as a kind of fixed dimension, and then things just, for some reason, fill out that dimension according to laws of nature. In Aristotle's picture, time advances because things are acting on each other and changing. And so time is always the measure of change. It's ontologically or metaphysically posterior to change. And change is therefore always directed. It's always change from one state to another, which means that time has an arrow at the most fundamental level. You don't have to sit back and say, wow, why does time have an arrow to it? Time has an arrow because it's the measure of change, and change is always directed. So from an Aristotelian point of picture, there's no problem of the arrow of time. It's built in at the very beginning. Teleology. Now, this is, of course, something that there's a lot of confusion about. People think, oh, it's Aristotelian stuff, all these weird teleologies in nature, how strange. But in fact, it's not that strange. Once you have powers and potentialities and directed change, as I just described, you have teleology. There's nothing more to teleology than that. And I think it's actually quite clear when you look at Aquinas, for instance, when he talks about, let's see if I can find that real quick. Yeah, this is in the Summa, Part 1, question 44. Every agent acts for an end. Agent, of course, any kind of natural thing that acts for an end. Otherwise, one thing would not follow more than another from the action of the agent unless it were by chance. So the very fact that things have powers that produce predictable, reliable effects, that's teleology, right? There's nothing more to it than that. And that's built into the Aristotelian picture. So a thing is supposed to act and react according to its own powers and potentialities. That's what teleology means. Now, potentiality, and this has been noticed recently in analytic metaphysics, as Brian has mentioned, that talking about potentiality and powers already introduces a kind of intentionality into the world. Because a power can exist and be ordered to a particular end, even if that end is never actualized. Right? So you've got a little electron out there in the middle of the intergalactic space somewhere. It never encounters any other negatively charged particle. Nonetheless, it has the power to repel negatively charged particles. Right? That's teleology. That's a kind of proto-intentionality built into nature, according to Aristotle. And so teleology in biology, and then ultimately in ethics, when you get to the Nicomachean ethics, all that is merely the application of this scheme to living things and to human beings in particular. Now, of course, obviously our rationality and all that makes a difference, but there's a continuity. There's an ultimate unity there. All right, good. All the Aristotelian scholars are nodding as I say this, so I'm feeling good so far. So finally, we get real agency at multiple levels, right? Composite substances are not mere heaps of subatomic parts, right, because of that formal dimension of causation. In particular, the biological form, or soul, as Aristotle puts it, contributes irreducible powers to the whole organism. And these, of course, include the obvious things like perception, voluntary motion, knowledge, deliberation for us. So it's not a form of dualism. The soul, the form, doesn't do the thinking, right, particularly speaking. The form enables the whole person to do the thinking, right? So the form is the thing that's conferring the powers, these holistic powers, upon the whole substance. Okay, so that's my quick summary of the Aristotelian picture. Now, in the late Middle Ages already, I think it starts with Scotus, maybe certainly with Occam, you begin to move away from this Aristotelian picture, the philosophy of nature. And of course, it accelerates during the scientific revolution of the 17th century with Galileo, Descartes, Bacon, and others. And there's going to be 5 elements I'm going to talk about here real briefly. Introduction of matter, the abstract laws of motion, the rejection of form and teleology, dualism, and the triumph of microphysicalism. So, again, we'll march through that really quickly. Introduction of matter as such. So for Aristotle, matter was always a kind of abstraction. It had no nature of its own. And also matter is a sort of relation. That is, something is the matter of something else, right? So the bones and teeth and so on that I have are matter of me. There's not such thing as just absolute matter as such, at least not with any real nature in Aristotle. And Scotus already begins to change that and replacing this relational conception of matter with a more substantive one. There's just matter, right? And then the matter has to have some sort of nature. And then eventually that leads to a notion that matter might just exist on its own, which, again, you would never be inconceivable in the Aristotelian framework. Now, once you have that sort of picture, then, of course, it's natural to start thinking about replacing the natures of things grounded in forms with laws of motion. So let's just think of matter then as having only quantitative features, and then we have laws of motion that tell us how that quantitative matter moves around over in time. And Descartes, of course, the paradigm of this, right, where you've just got quantity of matter, which is space that's filled, and then some kind of law of conservation of momentum, and that's it, right? Everything else is just a byproduct of that. And associated with this, I think, is an interesting sort of sociological fact, which is there's a move towards a kind of pragmatism. And you see this really in Descartes and Bacon very clearly, that what we really need to be after in science is not understanding the world, but changing it. It's kind of proto-Marxist kind of a picture here, right? We want to gain control of things. And so, from that point of view, who cares about forms and essences in teleology, right? We just want to get at the engines of nature. We want to figure out what we have to push and pull to make things happen, right? And Bacon said, look, teleology is just intercepting the severe and diligent inquiry, right, of all real and physical causes, right? Sort of letting the nature off the rack for a minute, right? When you need to be extracting your secrets from her. And understanding teleology, in essence, is it yields no control. It doesn't intervene as an actual and efficacious law of nature, says Bernard, and therefore, of course, it's no good from a modern perspective. And this finally leads, of course, to sort of dualism. I mean, in a natural world of uniform matter, obeying exceptionalist laws, what room is there for human thought or agency? Well, we can go with kind of dualism. We could say apart from all that, there's little human minds as well, and then they have to interact with the physical world in some way, maybe through the pineal gland and all of that. And all the teleology and agency in the world gets relegated to this human soul. But these mental entities end up being sort of extraneous danglers in the physical world, as I think that's J.J.C. Smart's term for it. How can they act on matter without a miracle? Very natural to end up with a sort of austere materialism of the 19th and 20th centuries and just get rid of the mind altogether or reduce it to something else. And then all this culminates in what I'm calling the triumph of microphysicalism in the early modern period. So every truth, causal and otherwise, about any macroscopic thing, including you and me or whatever, animal, is wholly grounded in and explained by the microphysical facts, including the intrinsic properties of the microparticles and their spatial relations and positions and velocities against a uniform background of space and time. You give me that, you give me everything, basically. Now, it may well be that for computational reasons we can't do this, or maybe our eyes aren't sensitive enough to sort out all the microphysical facts, but a Laplacian intellect with unlimited observational access to nature and unlimited computational power would just look at the microphysical facts, and that would be everything. It could then compute and figure out everything else on the basis of that. So it licenses the ontological reduction of macroscopic things to their microscopic parts, right? So maybe practically speaking, we don't reduce them, but in fact, ontologically, there's always a kind of reduction there in the background. And this leads to a whole kind of narrative, right, where we can reduce political science to individual psychology to biology, biology to chemistry to physics, and everything to particle physics, right? So ultimately, you get the unity of science kind of picture in the mid-20th century. The real science is pure particle physics, and everything else is stamp collecting, I think is Rutherford said, right? It's just filling in details once you've got the real scientific power. Okay, so the quantum counter-revolution. 4 phases here. So I'm arguing that what we learned with the quantum counter-revolution is that the scientific revolution in the 17th century was wrong about really fundamental philosophical principles, the ones I just talked about. We get a kind of revenge of teleology. We get a holism, top-down, holism through entanglement. We get the measurement problem really upturns the whole priority of microphysical over other domains. And we get a reification of potentiality and actuality, so it brings back the key ideas of Aristotle's metaphysics once again. Revenge of teleology. So classical mechanics could actually be formulated one of 2 ways. We can think of it in terms of Newton's laws of motion and the sort of parallelogram of forces that we learned in high school, right? So forces are kind of pushing and pulling the matter around, and the trajectory that things take are determined by those forces that are acting on each particle at each point in time. Or you can also think about it in terms of a kind of analytic or Hamiltonian approach, where what you do instead is you look at the boundary conditions and you impose a constraint of conservation of energy. So it's looking at the system more holistically rather than atomistically, as the Newtonian method does. And it turns out you can do either one of those in classical mechanics, and you can sort of prove that they're equivalent. And so typically what early modern people think, what modern scientists think, is that the first represents reality, really, and the second is just a kind of convenient tool for calculating what the particles are doing under the influence of these forces. Now, the latter involves some kind of holistic, and I would say even teleological notion, like a least action principle. So not only do we conserve energy, we also do so in a way that minimizes action, or something like that. there's some kind of a minimizing or sometimes maximizing that takes place. And it's a minimizing, maximizing that pertains again to the whole trajectory, right? So rather than talking about how things get pushed and pulled, you say, what's the best path to get from point A to B? And that's the path that the system will take. Now, what's interesting is when you get to quantum mechanics, the first kind of picture really is impossible. We can't really talk anymore about individual particles being pushed and pulled by forces in a Newtonian picture. Everyone does something that's based on the second, which is a kind of Hamiltonian approach. And this shows up either in, let's say, Feynman's path integral kind of picture, where he very explicitly refers to the least action principle to pick out the right path, or through the Schrodinger equation, which although it is a differential equation, it's based on the integral equations of the Hamiltonian approach. So it's holistic and teleological in the end. You also get holism, right? So Schrodinger says this is the characteristic trait of quantum mechanics, and entanglement enforces an entire departure from classical lines of thought. And of course, when physicists say classical, they don't mean classical. They don't mean Aristotle. They mean Descartes and Bacon and the 17th century. So this is really what he's talking about. Now, when two systems are quantum entangled, say two particles, the quantum state that determines their properties cannot be decomposed into the product of the states of the separate parts. Right? So in other words, you can't tell me what's the state of particle A, what's the state of particle B, how far apart are they, how are they moving, end of story. No, you also have to tell me how are they entangled. So there's an element of the whole system that's irreducible to the various parts. And this shows up, it was an inseparable part of quantum mechanics, inseparable sort of feature of it. So there's the famous Einstein-Podolsky-Rosen thought experiment, which has been since subsequently confirmed empirically by the sort of aspect program, where you've got two particles. I think I've got a slide here. I guess I got them slightly out of order here. And here's the actual picture. There's a source here where you're producing two particles, let's say 2 electrons, and they're sent off in opposite directions, and then their spin is detected in either site A or site B, let's say. And these two sites could be very, very far apart. Could be like across the cosmos from each other, right? They could be in such a situation that there's no possibility of a kind of communication between the two, right? And it would take too long for the light to bounce back and forth, right, between the two sites. And you can then, in this sort of picture, at each of these two sites, you can choose, once the particle gets there, whether to observe the spin in dimension x or y or z. So in each of the 3 dimensions of space, you can pick each of the 3 dimensions of space, there would be 3 different measurements that you could take of the particle when it arrives. Right? And what John Bell showed, actually, from the EPR experiment is that the results that you get, the probabilities that you get of the result in one side, is going to be something that cannot be made independent of the setting and the results of the other side, no matter what sort of factor lambda you try to hypothesize, a local factor that's supposed to determine things, right? So anyway, I'll try to explain. Let's see if I have a flip chart or anything. Here's the way that it works. I'll try to summarize this real quickly. Going back to the thing here. So if we measure exactly the same dimension in both sides, so we both decide to measure x, okay, we will always get opposite answers. So up here, down there, up there, down there. There's perfectly anti-correlated between the two. Okay. Now, if we measure different dimensions, x and y, given that perfect correlation, which suggests that, that somehow or other you might think the correlation means that the two particles leave here, one already has the spin up in x dimension, right? And the other already has spin down in x dimension, or something like that, some kind of information that they can carry, so that when I measure x here, it says, I know I should go up, and he says, oh, I know I should go down, so we can correlate, right? So if you assume that that's right, that there's some kind of local information that's carried by the two particles, then you could ask, well, what happens if we measure in different dimensions, right? x and y, or y and z, right? And if you look out, if you do the mathematics of it, I mean, there's just two possible results here, up and down, and three different dimensions, right? So no matter how the instructions go out, you're going to get disagreement at least 1/3 of the time, right? Because you can go up, up, down, or down, up, down, or whatever. And if you measure two of those dimensions, then in 1/3 of the case, you'll get the same answer, right? In the other two, you won't. So at least 1/3 of the time, you should get answers that disagree. And what's weird is quantum mechanics says you get different answers only 1/4 of the time. And so that's the violation of Bell's inequality here. So what it means is, the only way to explain these results is that somehow or other, the particle at one side sort of knows what you're observing at the other side, right? So that it knows if you're observing x and y over here, I need to make sure that 3/4 of the time I give a certain answer, right? And and Bell just proves there's no way to explain this in terms of local factors, right? So there's an irreducible holism, an irreducible inseparability of the thing. And again, I think from an Aristotelian point of view, it's not that surprising, because we can think of these two particles, as I'll explain in a bit, as really being two accidents of, or actually a single accident of a single substance, right? So the source here is the substance, let's say. The two particles are parts of a single accident, or a single sort of power or potentiality, right, of the source. And depending upon what settings you put on the two ends, you get different powers expressing themselves, right? Now there is a kind of communication in a certain sense, right, instantaneous on this sort of picture, because when I choose to observe something here, I'm sort of forcing that whole accident to move in a particular direction so that the appropriate kind of result can be observed on the other side. But that's not really surprising from an Aristotelian point of view, because whenever you act upon a substance, typically you're going to affect the entire substance in certain ways. And so the substance is extended in space, so you get kind of instantaneous effect here through the individual substance that's uniting the two sides. Okay, so anyway, that's my little spiel on that. So if we try to think of the two experiments as somehow influencing each other causally, as if there was some kind of signal that's being sent from one to the other, some kind of little particle that carries the information from one side to the other, will violate the special theory of relativity, because that little particle, that packet of information, would have to go faster than the speed of light. So instead, you have to think of the two widely separated particles as forming a single undivided whole, capable of a sort of instantaneous action or passion at a distance. And again, I think this does involve some kind of modification, I think, of the Aristotelian conception of the relationship between the location of a substance and its accidents. There's an analogy here, I think, perhaps with Aristotle's idea that a colored object sort of communicates its accident of color into the medium. Although I think it's not clear to me whether, for Aristotle, that accident then becomes an accident of the medium, or does it remain an accident of the substance? Quantum mechanics would say it should remain an accident of the substance. Right? So the two particles, as they spread out, remain accidents of, or a single accident of a single substance throughout the process. Finally, next we get to the measurement problem. So in quantum mechanics, we rarely assign a definite property to any particle, and it never assigns a full range of values to all the parameters of a given particle. So you can't assign both position and momentum, let's say, to each particle at each point in time. Instead, what the theory does is it assigns probabilities to certain experimental outcomes. It tells us what the probability is of certain sorts of results. But the theory itself is completely silent on what this measurement amounts to. So if you look at the original theory, at least, it's as if the microphysics is saying, I'm not complete. I'm not a complete description of reality. Because once you get down to this microphysical level, all I will tell you is you will see certain results at a classical macrophysical kind of level. Right? So the very description of reality that you get in quantum mechanics is anti-microphysical in some sense, at a very deep level. So, for instance, if you assume that the measurement device itself, or any other kind of, either the macroscopic instrument or the observer, is merely a bunch of quantum particles, then you get a kind of contradiction from quantum mechanics. And this is the thing that Schrödinger's cat sort of illustrates. You have some sort of quantum event here. A particle is emitted by radium or something like that, and the theory tells us there's a probability that it'll be emitted and a probability that it won't be within a particular period of time, right? If it's emitted, it causes the hammer to fall, breaking the glass, releasing the poison and killing the cat, right? And if it isn't emitted, the cat survives, right? Now, if you think of the cat itself as merely an aggregate of quantum particles, then what happens according to quantum mechanics is that you start out with the system up here in what's called a superposed state. So it's a state in which the particle is both emitted and not emitted, with certain probabilities attached to each state. And then by virtue of the entanglement here, the cat is also going to end up in a superposed state of being both dead and alive. So the quantum mechanics does not give us a definite result here. The quantum mechanics just sort of pushes the indeterminacy into every quantum system. And if the observer and the instruments are themselves merely quantum systems, then you never get a definite result, right? And that seems to be a kind of contradiction. There's been some work recently, the paper actually just came out, I forgot to write it down, sort of developing Wigner's friend into a real logical puzzle here. So here's another way of thinking about the paradox. So you've got Wigner's friend, this is Eugen Wigner came up with this idea, and he observed some kind of collapse of a quantum result, right? So the particle could either go to the left or the right, and he sees it go to the right, I guess, right? And at that point, he would say, aha, it's when I observed it, right, that I sort of forced the quantum particle to choose whether it should go to left or right, right? And so at this point in time, at which the particle, the quantum wave function collapses or resolves itself in some way, right? But then Wigner says, but suppose I'm outside the laboratory, and now I think of Wigner, my friend, as also a quantum system. So he's just a part of the same quantum system. So then, from the point of view of Wigner himself, as long as he keeps the door shut, what really happens at this point is not that Wigner's friend sees it go left or right. It's rather that Wigner's friend goes into a superposition of seeing it both left and right. And it's only when Wigner himself opens the door and looks at his friend that the wave function collapses to one definite result. So you get and then Wigner and his friend talk about it afterwards, and Wigner's friend says the quantum wave collapsed at T1, and Wigner says, no, it happened at T2, a few minutes later. And so there's a fundamental disagreement about what's going on at the quantum level. Now, what's the typical answer to this among philosophers? The most popular answer these days is some kind of many worlds answer. So the idea from Everett is, Hugh Everett proposed, that whenever this kind of macroscopic observation occurs, the world splits into two or more separate versions, with each experimental result actually happening in one of those two versions, one of those two branches of the world. So this is what you have to do to preserve the idea of microphysicalism, that everything is just composed of microphysical particles. If you take that seriously and you take on quantum mechanics, you have to say this. That is, that at the macroscopic level too, we split. We experience these superpositions. And the world is constantly splitting. And so there's two problems with this, as we'll see. One is that the quantum formalism itself does not include any such branching worlds. And I sort of alluded to this at the very beginning. The quantum formalism itself doesn't say anything about the world that we observe and we see. All that's got to be somehow imported into the formalism. It just gives us this vector fluctuating in a high-dimensional space. So the Oxford Everettians say that you can treat these worlds as emergent phenomena, and they appeal to some process known as decoherence, which we can talk about during the discussion if you like. So all the worlds are equally real, and they're constantly splitting when we interact with the quantum world in various ways. So the cat is both alive and dead, and I observe the cat dead, I observe the cat live. Both things actually happen, just on long different branches. That's the picture. Now, there's a couple of problems from the Everett point of view, and one is it's really hard to see how they make sense of the probabilities that attach to these branches. Right? So the quantum theory says 1/4 chance this way, 3/4 chance that way. Everett seems to say probability 1 this way, probability 1 that way. They both happen with certainty. So what does it mean to say that one happens with more or less probability? Now, Wallace and others have tried to come up with clever ways using decision theory to answer this, but they don't work. So I don't have time to explain. Read my chapter in the Koons, Simpson, Tay book. And also Hugh Price has made the same kind of point, which is that Everettian, the decision theory solution only works if you assume that I can only care about one world at a time, that I can't care about things that happen across worlds. But if the worlds are all equally real, there's no reason why I shouldn't. There's no reason why I shouldn't think, gee, I'd like to kind of make sure we have equal utility across branches or something. But as soon as you take an interest in that, it spoils their decision theoretic argument, and you lose that. But there's, I think, an even more important problem, which is if we ask, what does it mean for the familiar world to emerge from these quantum operations? What does it even mean to say the cat's alive or dead on these different branches? Where did they get that? And the way they do that is to say, look, there's just some kind of mapping from the quantum formalism to our description of a world in terms of cats and people and so on. And as long as you have a kind of structure and probability-preserving mapping, you've got an emergent world. That's the claim by the Oxford Everettians. But then, as I showed in that same chapter, any consistent story whatsoever, so long as it has the right number of entities, can be mapped into the quantum formalism. So Lord of the Rings, Harry Potter, and whatnot, those are also emergent in exactly the same way that our world is emergent on Everett. So you get way too many worlds in the end, right? Every kind of consistent story ends up being part of the world. So how do Aristotelians fix this, right? So for Aristotelians, 2 steps here. First of all, there are a fixed number of essences or natures that are metaphysically given to us, so to speak. And those natures are the ones that determine the way in which the macroscopic world can emerge from the microscopic world. So you get a microscopic world, a world like ours, only because the world already has essences of humanity, cat, donkey, water, and so on, that enable us to get this macroscopic phenomena. So donkeys, bodies of water, yes. Elves, mithril, unicorns, no. Right? There are no forms. There are no essences that correspond to those mythical things. And so you don't get a world that emerges along those lines. But then once you have the forms in the picture, they can do another job for us too. The form can then actualize which of the branches is the real one. Right? This is another thing this interesting thing goes wrong with Everett, I think. The reason that Everett gets himself into this fix with probabilities is that he's lost the distinction between the actual and the potential. That's disappeared, right? And if we go back to the Aristotelian framework, we can say, yes, you're right, all those different branches are real in a sense, but real only in the way of being potential. There's only one that's actual, and that's why you get the probability theory working out rightly, right? The probability 3/4 is the probability that this branch will be the actual one, the uniquely actual one, as opposed to the others that are really potential. Now this makes room, actually, for free will or downward causation, because it means that these forms, which are determining the emergent world, can also determine which branch becomes actualized. So the quantum world is constantly putting out there a range of potentialities, right? And then I, using my free will, can choose which of those potentialities to actualize. So real difference making can be attributed to macroscopic level once you go to this route. So this is something that Alex Proust and I have developed this a bit. We call it the traveling forms interpretation. So the idea is you've got this, as Everett describes, this kind of vast branching tree of potentialities, and you have forms that are actualizing one of those branches and sort of moving through the tree progressively with time, actualizing the actual history of our world. So free choice can affect quantum reality. A lot of people thought about this in the 80s already. One of my colleagues, Robert Kane, and his student Robert Bishop were working on this. And I think more recent work really confirms and corroborates their work and suggests that it can actually make perfectly good sense. So as I mentioned, we get a redefining of potentiality. And this is something that Heisenberg actually talks about in 1958. So Heisenberg is actually the first one to recognize, I think, that the quantum revolution vindicates Aristotle. This is in his book on physics and philosophy. He says, look, before the quantum revolution, we had pretty much gotten rid of potentiality. Right? You could just tell us what's actually going on in the world. Where are the particles and how are they moving? You plug in the laws of nature, and that tells you what actually will happen. you don't need potentiality and possibility. I mean, you can have it if you want to. So you can think of it as a kind of thought experiment. You can think of it as sort of imaginary fictional states or whatever. But in terms of actually explaining things, you just need the actual world. But as Heisenberg points out, quantum mechanics says, no, that won't work. The actual world is not enough information. You need the information about the potentialities as well. And that, I think, is the most fundamental vindication of Aristotle of all, actually. It's the thing that most dramatically takes us back to the Aristotelian future, as I'm getting to here. So by restoring potentiality, teleology, and holism, quantum mechanics really reopens the question of the efficacy of sensation, desire, rational thought. And to solve the measurement problem, we have to bring back Aristotelian form, formal causation. In order to cut down the number and variety of emergent worlds, to get rid of Harry Potter and keep our world, and in order to select the one actual branch from the many that are permitted by quantum mechanics itself. So is it just a form of polite materialism? So when Bernard Williams is talking about hylomorphism, Aristotelian philosophy, I think this was back in the 70s, he says it's just polite materialism, really. I mean, it's just matter doing all the work, and then you can introduce form as a kind of, rhetorical gesture towards everything else. And my answer is no, right? Because Aristotelian form is not merely the spatial arrangement of Democritean particles in space. That's the wrong way to think about form. That is not what form is. Form makes a real difference to what actually happens, right? The particles in quantum mechanics have no determinate arrangement in space. Right? That's the fundamental thing, right? And they don't even have individual identities. There really aren't individual particles anymore, right? They exist merely as indeterministic potentialities for substances to act on other substances. That's it. And that's very, very concordant with an Aristotelian picture of the world. Particles, therefore, are only virtually present in substances, just as elements were only virtually present in chemical mixtures in Aristotle's chemistry. They are activated when substances interact with other substances. That's when the particles become actual. Ordinarily, they're in a state of mere potentiality. They're simply virtually present within the whole. So anyway, I'm running a little late on time, so I apologize I had to rush through this a bit. We can think about substances, parts of substances, on two different dimensions. We can look at those parts that are actual versus those that are merely virtual or potential, right? So in my own case, I think I actually have a heart and a hand, and so on. Those are those on the actual side. On my view, the many particles, electrons, atoms, and so on that compose me are only virtually present. They're not actually present unless you activate them through a particular experiment, right? So you can sort of force them to become actualized. You can use an electron microscope and find one of my atoms, right? Once you've done that, you've sort of actualized that particular atom, but the rest remain in a virtual state. We can also distinguish between those parts that are integral and those that are independent. So there are many parts of me that couldn't exist except as parts of me. Right? And again, the hand, right? Couldn't be a hand unless it's part of me. It's an X hand if you cut it off, right? It's not the same thing anymore. So it's no longer the same entity, in fact. As far as actual and independent goes, I think the Aristotelian is going to want to say, really, there aren't any such things, except perhaps in the sense of remnants of extinct substances. So if for instance, there's this woman, Henrietta, for her last name, whose cells are still going even though she's been dead for 50 years. And the cells aren't substances, but they're sort of remnants of her substance. And so they have a kind of existence, not completely independent, because I think they could exist only because they are still remnants of her substance. But they nonetheless are independent in the sense that they can exist when she doesn't exist anymore. And I think that does happen. So similarly, when we look at light from extinct stars, right, we're seeing accidents of substances that no longer exist. Right? So the accident is persisting after the substance no longer exists. And then there are certain thermochemical substances in me that are virtual parts of me that could become independent if I were to die, or if they were to be excised from me or something like that. Now, what are the world's substances? So, from an Aristotelian point of view, organisms are the paradigm of substances. They're the sorts of things that have the kind of unity that we would expect. But I think we have to recognize the existence of inorganic substances of some kind. We can't just have organisms alone, because we want the we want to meet something like what Jonathan Schaffer calls the tiling constraint. We want the material world to consist entirely of substances that don't overlap, that aren't parts of each other, but also we don't want to have a whole lot of stuff that isn't part of any substance. Maybe some exceptions. So as I said, these remnants, I think, are the exception, but even that's not enough. Okay, so let's see. Probably can zip through some of the technical details here. Let me just say something about, let me jump up to and say just a few minutes here before I run out of time about chemistry and thermodynamics, because I think this is also quite interesting. So, again, in the pre-quantum world, right, the thought was that chemistry was really just physics on a larger scale, right? Just tell me where the electrons are at any given time, where are the protons, where are the neutrons, where are the electrons. That gives me a molecule. The shape of the molecule gives me the chemical properties, right? So it's all reducible to the physical level. Now, it turns out in quantum mechanics, though, something interesting happens. And that is that if you represent a system as having only finitely many parts, finitely many component systems, as we imagine things have only finitely many atoms or particles, let's say, you get a result that's called unitary equivalence, which means that you can't represent macroscopic differences that involve symmetry breaking of any kind, right? So, for instance, in classical mechanics, you can have symmetry breaking. And in fact, it turns out classical mechanics is not completely deterministic, contrary to what people thought. John Norton, a few years back, has an article which proves this. So, if, for instance, if you were to balance a pencil on its end, and say it's a perfectly symmetrical pencil, right? And there's no disturbances whatsoever, no vibrations. According to Newton's laws, the pencil could stand there forever, or it could fall down in any given direction, and any one of those results would be consistent with Newton's laws. So Newton's laws are not actually deterministic in that particular setting. But quantum mechanics, pure quantum mechanics, is deterministic. Pure quantum mechanics says the pencil falls in every direction at once, right? And so there's always a single determinate result, right? And so that means that you don't get any kind of spontaneous symmetry breaking with pure quantum mechanics. So how do they get around that? The way chemists do this is they go to what's called the continuum limit. That is, they sort of pretend or they model the system as if it had an infinite number of particles, an infinite number of subsystems. And at that point, you can actually get a much more complex algebra of the properties. And you get something that results in the breaking of symmetries. So what's going on from an Aristotelian point of view? See, I say that these models that take us to the continuum limit are the chemist's way of getting at the fact that there are substances out there in the world, right, with their own chemical forms that are irreducible to the physical facts about the particles that make them up. And so, again, we actually get irreducible chemical form, which is needed to do things like this, to explain phase transitions, right? Because you can have the substance can be at the same temperature and pressure, and parts of it be solid, parts of it be liquid. That's what we mean by phase transition, right? So the chemical composition, the temperature, and the pressure don't tell you whether it's solid or liquid. Pure, finite-based quantum mechanics can't represent such a situation. It's impossible. There should be two such states in that same condition. You have to go to the continuum limit. You have to go to this new kind of representation. And that means basically what you're doing is you're importing a new kind of form into the picture, a form of solidity, a form of liquidity that's over and above the form of the individual particles. Molecular asymmetry, basically the same thing. You don't get, let's see, I guess here's the quotation. The Schrodinger equation is spherically symmetrical, right? So there's no way the Schrodinger equation can explain how you get a difference between left-handed and right-handed molecules, let's say, because those are symmetrical, right? So in order to break the symmetry, you have to go to the continuum limit, which again means that you're basically accepting that the microphysical is not complete, that it can't provide us with all the explanations that we want. And so in terms of identifying these things, in a couple of papers I've called these things thermal substances. So my conjecture is that in addition to organisms, there's also inorganic substances we call thermal substances. Where exactly are they? What are their boundaries and so on? That's hard to say. It's a bit of philosophy of nature program, I think, that we need to work on. Symmetry breaking provides a criterion. So I think, in fact, that when ice, let's say, melts, that's a substantial change. You get a new thermal substance, right, because you're breaking the symmetry at that point. Obviously, chemical change, I think, would be sufficient. Quantum entanglement is sufficient for synchronic identity. So if two particles are entangled, they're parts of the same substance. Now, some philosophers have taken entanglement to the extreme to say that really there's just the one substance. Jonathan Schaffer takes this view. There's just the cosmos, the one single substance. Well, as an Aristotelian, I'm going to try to resist that, I think. I want to say that you and I are substances, right, and not just parts of the cosmic substance. And it turns on this question about whether there is collapse of the wave function or not. If there is collapse, as I think there is, then entanglement will itself collapse at certain points, and so we could use entanglement as a criterion for substance identity. Substances, though, can be of any size. So, although I talked about macroscopic, in fact, it's quite possible for these thermal substances to be really, really small, maybe to be composed of a single atom or something like that. It's not that the distinction here, the distinction here is between substances and their integral parts, not between the macroscopic and the microscopic, which I think is where Bohr actually went wrong. And substances, no matter how large, can also have quantum properties. So it's not as though when you get really big things, there's nothing quantum going on, and when you get really small things, there's no substances. That's an oversimplifying. You can have quantum phenomena at a large scale because these large things have quantum parts, which affect their behavior. And conversely, you could, in principle, have substances that are microscopic, although they'd be undetectable by us. Right? The substances that we need to work with in the laboratory are macroscopic. Okay, so I'm going to go ahead and stop there, and hopefully that's enough ideas for you to react to. And I think I'll just take the questions myself, Ryan, if you don't mind, unless you decide I need to be reined in or something.